Greetings, everyone, and welcome to today's webinar featuring the paper Factor Graph Optimization for GNSS-INS Integration, a comparison with the extended Kalman filter, published in the summer 2021 issue of Navigation. Today's webinar will be presented by Dr. Li-Ta Xu, one of the paper's authors. Dr. Xu received his BS and PhD degrees in aeronautics and astronautics from National Cheng Kung University in Taiwan in 2007 and 2013, respectively. He's currently an assistant professor in the Interdisciplinary Division of Aeronautical and Aviation Engineering at the Hong Kong Polytechnic University. He is a member of the editorial board in GPS Solutions. Please note that this paper is available to download from our website free of charge. We greatly appreciate the time and work that Dr. Xu has put into preparing for this webinar. Following the presentation, we'll take questions. To ask a question, you can click on the Q&A button in your navigation bar for your Zoom client. So thank you for being here, and now we will turn the time over to Dr. Xu.
Thank you, Rick. And can everyone hear me clearly? So thank you everyone for joining this webinar. I'm very excited to share our research outcome on factor graph optimization for GNSS-INS integrations. And we're going to compare it with the extended Kalman filter. So I would like to thank the first author, Dr. Weisong, to conduct this work and provide a lot of insight for us to share this research result. And also the second author, Tim, who was a visiting student in our lab for a couple of months. He also shared a lot of insight on FGO. And Xiwei to collecting the data as well. All right, so let's crack in. Let me see. Okay. Right. So GNSS and IS are complementary. Everyone noticed, and that there's a lot of papers since 1980s using GNSS and IS integrated by EKF. But since 2012, a lot of integrations using factor graph optimizations. So we want to highlight the first paper using the factor graph in GNSS positioning is from Nico and Professor Peter Pressel. They use GNSS, they use the robust graphical model for GNSS-based localization in urban areas. Then the CMU team using the factor graph in inertial navigation system. This opened a new door for robotics. Then Professor Jason Gross and Dr. Ryan Watson also using FGO in precise point positioning, PPP. Then Professor Lu Mingquan's group also give simulations on robust graph optimization realization tightly coupled. So there's a lot of more, so we just highlight a couple. But for us, it's like, okay, this is new technology, sounds so good. So we're trying to implement this technology and see how it goes. So here is a quick result. Then we test in 2012 and we publish in ION Genesis Plus, the conference we all go. Then you see that this is the environment that we test in. The black one is the ground truth, and the red one is GNSS single point positioning, which is weighted least square. And you can see EKF is the green one and FGO is the blue one. So clearly FGO outperforms EKF, but the question is why? So this is one of the contributions of our paper. We're trying to answer why factor graph is better than EKF. So first of all, we dig into a lot of papers and books. We realize that, okay, EKF and FGO, they all come up with the maximum of posterior estimate, which is NAP estimate. So we list a very standard equations here. Okay, so when you see something like this, okay, let me have a pen. So we're cracking with our GNSS context, okay? Z is the measurement. So here is a GNSS measurement. U is the input, which regarded as INS input. X is the state that we estimate. So in this MAP estimate, we want to find a subset of X. X means like your position velocity. We're trying to find a subset, meaning from epoch 0 all the way to K, that we can achieve the maximum posterior probability in condition of a set of the Z measurement from 0 to K and a set of input measurements. Okay, that is our goal. We're trying to find a maximum posterior probability. Then we're using a very simple Bayer theorem. We can get, okay, so the posterior probability is positive proportional to likelihood and priori probability by propagations. So this is all what we know, and using a lot of filters. So how EKF is an NAP estimate? Okay, starting with EKF, maybe we're starting with KF. Okay, so this is a maximum posterior probability estimate. This is the probability of posteriors. In EKF, what they do, the first assumption is first order of Markov chain. meaning that your state here is only related to the previous epoch of the state by propagations, then and also related to the current epoch of likelihood. So if we're using EKF, we know that, okay, the priori probability is by propagation. So please take note of the color here. In the blue color you see here represent priori probability. So the priori probability is actually propagate based on the previous posterior probability. Okay, this is the first Markov chain. Then the posteriors is updated by the measurement. So you can see the posterior, which is the red one, is your prior probability updated by the likelihood. All right. So this is very clear. We're using recursive filter to update the posteriors by propagation and update. Then the second assumption is like, okay, we do system modeling and Gaussian noise. Then you can come up with the equations that we know for so many years. You can see here, the green one here is the propagation model, and the orange one here is the measurement models. And here is the likelihood. Then this is priori. Then this is the update. But the question we frequently ask, then why this is a maximal posteriors? If we dig into one of the paper, I'm not sure if I can hide this one, but anyway, if we dig into one of the paper by Dr. Chan's, this paper here, then actually he proved that EKF is an NAP. So bear with me because I copy all this equation from the reference here. Okay, so X again represent the state. So here we're using Y to represent the measurement. Okay, so you can see this one is again posterior one, and this is likelihood, this is priori probability. Then we have the assumption that, okay, so this is the model of the measurements, and we have a Gaussian noise, which is the assumption 2 that I mentioned earlier. Then you're trying to solve the PDF by expectation. This is what you got, and this is the covariance. So the whole PDF become a Gaussian distribution. Again, the orange one is the likelihood. How about for the propagation? For the system propagation model, if we have F here, we have D as the Gaussian noise. Then we solve the PDF, the priori probability by PDF. This is again another Gaussian distribution. Okay. Then our posteriors is positive proportional to likelihood and priori. So we make the blue ones here, and we need the orange ones here. Then we got the red one here. So this is our posterior probability. How do we find the maxima of it? The very straightforward way is to do the derivative of it, right? We're trying to do the derivative of it. So we do the partial differential of this posterior probability with the state. And to make everything easier, because we got exponential here, we do a log here, it doesn't affect the result, make the calculation easier. So if we can find a derivative this equals to 0, then your X is represent to maxima of posterior estimations. By solving this one, if you want to check the duration, go check the paper. But by you solving these equations, then in the end, you come up with the EKF measurement update equation that we see frequently. Okay, so EKF is definitely an AP estimate. How about FGO? Let's go to our topic. How about FGO? Again, so FGO, it is also an MAP. Then we have also the posterior. This is likelihood. This is priori. This is propagation. Propagation is trying to supplement the priori. Okay, so they also do the same assumption, the system model, measurement model, and the Gaussian noise. Instead of making this as a recursive one, so you got a model here, you got a model here. The next step is they factorize this model. So they factorize this model, meaning that this model here, because we know it's a Gaussian noise, so we know that, okay, for your model minus your state here, then it become a Gaussian distributions. No matter it is the propagation, which is the green one, propagation, or no matter it is the orange one, the likelihood, it all become a factor. And for the initial probability, we give it 1, but it doesn't really matter in the presentation, in the implementation. Okay, so one thing here, very different from Kalman filter, is that instead of using the first order of Markov chain, he's using the batch data. Everything is used. Everything is used instead of just the first order of Markov chain. Okay, this is the first differences that we notice here. Then after we construct the factors here, we make the posterior probabilities is positively proportional to the factors multiplication of the factor of the propagation, which is the green one, and the factor of the update. Okay, the factor of the update. Then we're also trying to find the maxima posterior, meaning like we're trying to find the maxima posterior, a subset of X to find the maxima posterior probability. But in here, you usually see someone that to say like, okay, so in the other word, you're trying that the maxima posterior here is meaning to nonlinear least square. Why is that? Okay, so these factors here, because we also assume Gaussian noise, you got an exponential here, then you got a minus here. Okay, if I'm using a log to get rid of the exponential, and here got a minus here, so maxima, then we're trying to find the maxima posterior become the minimize the cos function. Okay, we're trying to minimize the cos function here. So in the other word, in the end, you only need to minimize this one and this one so that you can find a subset of X to minimize it, then it becomes an optimized solutions. So how to solve the optimization problem? As I mentioned earlier, so the maxima posterior because of the Gaussian distribution assumptions, so it become minimize the cos function E of subset of X. So this is how it look like. This is how it look like. So what we do is we do the nonlinear optimization iteratively to obtain the optimal solutions. Again, you give an initial guess, then you give a step, you find the Jacobian, which is the gradient of it. You can do simply like this, or you can using a more state-of-the-art Divenberg-Marquardt method, which is LM method to solve the problem. This is all the nonlinear iteration least square. Okay, you can use the method to find an optimized solution. So to this point, we can compare the theoretic comparison. What is the difference between EKF and FGO? They all have the assumption of the Gaussian noise. Okay, they all have the assumption of Gaussian noise. But in EKF, they have the first of the Markov chain, and FGO doesn't have. And in FGO, let me come back here. So because here, what we do is nonlinear optimization iteratively, meaning that we have to calculate the residual, and the residual is going to update to the result. So this become initial, and the next one is 1, this one is 1, this is 2, until that the threshold is smaller enough. So it do iteratively. Okay, so this is very different with EKF. So they solve the solution iterative by nonlinear optimization. This is what FGO do. Okay, so the main differences is we conclude FGO use the batch data, FGO apply iterative optimization. The very two different point. Okay, so quickly looking at this, the cons is that the computation is gonna be expensive. There's a lot of data there, and the process is pretty robust when two assumptions are violated. All right. So let's looking at our implementations. So IMU, which is meganometers, gyroscope, and accelerometers. So in fact, we're using the X-sense output. We call it the AHAS, but it's essentially an X-sense output to provide us 3D orientations. In the other word, in our INS mechanization, we didn't estimate the orientation. This is just for us to easier implement the solution. Okay, so this is just for us to make it easier. And after you have INS mechanizations, is control input, which is the U over here. And for GNSS receiver, we're doing the weighted square single pole positioning to give a PVT result. This is the loosely coupled one. And the EKF also estimate the bias and use to update the accelerometers. Okay, so this is our loosely coupled. To look at the model, our state is a degree of freedom of 9 by 1. So which is 3D position, 3D velocity in ECF, and also the accelerometer bias in body frame. Looking at the propagation models, so this is our raw accelerations, and this is our state, the accelerometer arrow states. So by doing this, and we have the rotation matrix from bodies to local, from locals to global, so we can make it as acceleration in ECF. Then we put it as an input here. And for our propagation model, pretty simple. Velocity multiplied by delta t, then you got the positions, then this is the position, very typical one, x, y, z, and accelerometer multiplied by delta t plus the velocity, very typical, x, y, z, and this is the 3 biases in body axis. And in measurement model, because this is loosely coupled, our solution directly is a positioning fixed x, y, z. So basically the model itself is just identity matrix. And for our R, I'm not sure what is this, but for our R, then it is h star multiplied by the user equivalent residual error. We put it as 10 meter. We set it as 10 meter here. This is for loosely coupled EKF. How about for FGO? FGO, we usually have to construct a graph. Okay, construct a graph, and each of one we call it an error factor, error factor, error factor. So we're trying to minimize all these error factors. So this is our objective functions. We have to maximize we have to find a subset of X to minimize the error functions here. Okay, for the green one is the GNSS factor. GNSS factor loosely coupled, so it's just one H here, loosely coupled. So again, very simple. This is position fixed. This is identity matrix. This is X. Simple. And for INS, the same. So you have the acceleration in body frames, and you minus the bias and the two rotation matrix, make it as an ECF, put it into the propagation model. The propagation model here, FINS, represent this one, which is accelerometer multiplied by delta t plus v in XYZ. Okay, simple. And the blue one here, the blue factor here is called emotion model factors. It's dealing with the second part of the INS mechanizations. So you see the v multiplied by delta t plus x. This is the second part, and also the bias is here. Okay, so this is how we construct the objective functions of the FGO. Then after you construct this FGO, currently there's a lot of solver to solve this nonlinearly squared problem. So what we use in this paper is GTSAM, which is developed by CMG, or you can use in Google Ceres to do this as well. They are all very popular solutions. Okay. Right, for tightly coupled, everything is the same, rather than that the measurements, it become the pseudorange and Doppler frequency. The rest is the same. Okay, for the modeling in tightly coupled EKF, state is the same, propagation model is the same. The difference is the measurement model. The measurement model, pretty straightforward. We have the satellite position and we have the state position. So this is basically the line of sight multiplied by the XYZ. If you do the first order Taylor series, and you got a clock bias here. So this is our typical edge matrix of the GNSS positioning. And in our noise covariance here, we because this is in the pseudorange domain, so we're using the weighting scheme of elevation angle and carrier to noise ratios to develop the weighting scheme. Okay. Then in tightly coupled FGO, the only difference comparing to loosely coupled FGO is the error factors in the pseudorange. So you become a pseudorange one, pseudorange one, pseudorange one. So in here, look at this. In here, that we have the pseudorange, and this is the line of sight, the line of sight unit vectors and satellite positions, and this is our state, and this is clock. So this is our model look like. Oh, one thing I forget to mention is this one. This one we call it information matrix. Basically, you can regard it as 1 over R, 1 over noise covariance in EKF. Okay, so in the setting, they were using everything the same with EKF. All right, so to here, I want to quick conclude that, in fact, in comparison to EKF and FGO, we're using the same model, the same noise covariance are used. The only difference is the way of implementing it, the way of the MAP estimation. Okay, so we want to do this because this can become a fair comparison in the experiment evaluations. Right, so this is our experiment setup. I hope I didn't go too fast because I have 30 minutes. I already using 15 of it. Right, so this is an experience setup. So this is our car, but basically we're using the span CBT to provide us ground truth. We're doing RTK as open sky areas. Then after we got the RTK fixed, then we quickly drive into the urban Kenya to using this fiber optics level of gyroscope to help us to maintain the solutions. And in addition, not only we're using span CBT Novatel, we also purchased the IE solution, which is Inertial Explorer, to make sure our ground truth is trustworthy. And for IMU, we're using Xsense level, MTI-10, which is a commercial level one, and GNSS, we're using uBlocks MAT. I think in this paper, we're using the constellation of GPS and Beidou, because there are lots of Beidou satellite in Hong Kong. Okay, so for FGO server, we're using GTSAM. For EKF, we're using roughly, basically Xigen. Okay, so let's looking at the performance comparison between EKF and FGO using loosely coupled. The blue one is FGO result, the red one is EKF. You can see the result quite similar, but somehow FGO is outperformed EKF a little bit. If we're looking at the 2D arrow, it means it's become from 9 meters to 7 meters, and the standard deviation is about the same. This is the 2D arrow. So you can see FGO improve a little bit, but not really a lot. So, and there is so this is roughly the starting point. Okay, so starting point, we drive like this, make a circle all the way to the end here. Okay, so in the beginning of the point that we can see that both EKF and FGO in loosely coupled have a big offset. The result of the big offset over here, it doesn't really improve that much for the loosely coupled. So we want to see what's going on over the peak over here. So we're doing the calculations of residual calculations. So how we calculate the residual is, this is the Z. I'm not sure if it's blocky, but this is Z, and this is our estimate solution. Either it's by FGO, it can be by FGO or by EKF. Okay, you can by FGO or by EKF. So in this loosely coupled one, this is in position domain. So we're doing XY. We're looking at the horizontal only. All right. So this on the left hand side, this is the residual in position domain. So you can see the blue one is FGO, the red one is EKF. So we observe is that, okay, over the first 50 epochs, that our error is big, but our residual is also big. What does it mean? It means that both EKF and FGO cannot find a subset. I repeat, cannot find a subset of the state that satisfy the constraint. They cannot find a subset of the state satisfy the constraint. The constraint meaning that the error factor that we list in the FGO formulations. Okay, so the performance is very limited for EKF and FGO in loosely coupled. But in tightly coupled, things change. So this is for tightly coupled GNSS-INS integration. Okay, so the red one is EKF again. So the blue one is FGO, and this is tightly coupled. You can see the result of FGO much smoother comparing to tightly coupled EKF, and the solutions in 2D arrow. So for your reference, loosely coupled EKF was about 9 meters, and standard deviation also about 7 meters. So it meaning that from loosely coupled to tightly coupled, it doesn't really improve that much in these cases. But for FGO, is improved from 8 meters to 3 meters, and standard deviation 7 meters to 3 meters. Bear in mind that the setting of the covariance matrix, the setting of the model are exactly the same between EKF and FGO. The difference is how we implement the maximum posterior estimations. Okay, so let's look at 2D arrows here. So you can see the arrow become much smaller, the FGO much smaller. So again, let's looking at the residual here, because we're doing tightly coupled. So the residual here is in pseudorange domain. Okay, pseudorange domain. So the estimation can be either by FGO or by EKF. Okay, FGO or by EKF. You can calculate the pseudorange residual. Okay, comparing with the pseudorange residual of EKF and FGO, you can clearly see that the FGO has the capability to find a subset of the state that consistent with the constraint. So again, the tightly coupled FGO is able to find a subset of the state that consistent to the constraint. Okay, so that's why the solution is much better. And the reason being is that tightly coupled. So if we're going back to our previous slide, you comparing with tightly coupled graph with the loosely coupled graph, what you can see is here. So for tightly coupled, if you got 20 satellites in a single epoch, then you add 20 constraints. And for loosely coupled, you always have only one constraint. So the number of constraints for loosely coupled and tightly coupled are very different for FGO point of view. Okay, so the more constraint, the better for FGO. We can quickly see this in loosely coupled FGO and tightly coupled FGO already. Okay, and a second thing we want to observe from the tables here is that okay, if you look closely enough, you find out that okay, at the epoch 200 over here, even if our residual is pretty small, but our error is still pretty big. So what's going on here? So the explanation is that we can find a subset of the state that comply with the constraint here. But this constraint may not be healthy enough. If you have a lot of unhealthy measurements, you find a constraint, you find a status, the consistence to those unhealthy constraints, your solution is still not good. So I want to say that FGO doesn't solving all the problem. You still have a good modeling of the multipath to solve the problem of we highlight here. Okay. Right, so I want to do more on the investigation why FGO is really improving, outperforming FGO. So if you remember our theoretical comparisons, that FGO has 2 advantages. First is using the batch data, right? It's not using the first order of Markov chain, using the batch data. Everything is considered for the optimization. Okay, but we want to get rid of this one. So meaning that we only using the single epoch or data in the FGO. We consider only this one in FGO. only 2 error factors in one epoch of estimation and see how it goes. And even if we apply this one, FGO still got the second advantage, which is it apply iterative optimization, nonlinear iterative optimization. So let's see how this one can really improve comparing to the conventional EKF. Okay, so we have to know that EKF doing the estimation recursively, it's not iteratively, they're doing recursively. So this is the main differences. Let's see what's the result look like. For the tightly EKF, this is the 2D arrow. So tightly EKF previously we mentioned is about 8 meters, right? But for tightly coupled FGO, there was window size of 1, meaning that we only losing a single epoch of data. The arrows is still about 5.18 meters, 5.18 meters. So you can see that in the first period here, the FGO still got a very big arrow, because at this epoch later you will see the data is not so good. The GNSS satellite, half of it is unlost, half of it is lost. So FGO cannot solve all the problem. But if you have some of the good measurements and more than the bad measurements, FGO did have a good performance. Okay, and if we keep increasing the window size from 1, which is the single epoch solutions, to 5 seconds of the window, which is we consider only 5 in the windows, 10s, 30s, all the way to the batch. This is how the performance improved, all the way from 5 meter, 4.5, 3, and it doesn't really improve that much after you have the window size of 10. Okay, so both of the advantage make the FGO outperform EKF. And we want to see even deeper into the solutions. So this is the 2D arrow. Different line here, meaning that the different window size. Okay, different window size. And over here, you can see this is the big peak you can see in the 1 second of FGO, which is only only consider the previous epoch and current epoch of the data. Okay, so you see at this epoch of the time that you have a healthy satellite roughly about 6, unhealthy satellite roughly about 6 vs 6 loss comparing to 6 unlost. So if you do FGO, it won't better. But if you're using the window size of 5, you can see the error reduce dramatically, because you can using the other data to leverage out the constraint here. You can using the other data to average out the error occurred in this particular epoch. Okay, so if you're looking at the epoch from 50 to 150, that most of the case, the satellite distribution looking like this. You have a few unlost, but you still got enough of the lost satellite to give you a good solutions. Here is 5 meters. So it meaning that over this area, you can still get it around 3 to 4 meters out of this environment. Okay. But if we look closely enough, they got a second very interesting situations here. Okay. So it's epoch D over here. Epoch D over here. You can see that we're using the batch size, which is we're using the window size 200 seconds, is really not outperforming the size of 30s or 10 or 1 or 10s. This is weird. We're talking about more data, the better, right? We're talking about more data should be the better. Why the window size, we make it as a batch, which is the blue line over here, it is actually not outperforming the window size of 30s. So this is what the question asked by the reviewer of navigations. By the way, navigation journal is one of the hardest journal I ever submit. I strongly recommend all of us submitting your good work to navigation. You can have a lot of good review and a lot of good comments to make you learn your own work. That's what I learned. Oh, sorry for drifting a little bit. So let's see why 30 seconds of window is not better. It's better than the batch optimization. So what we do is that we're doing an analysis. That because in our group that we know that in most of the case the multipass is not Gaussian. We all know that. In our experience, it's more or less like a Gaussian mixture model. Gaussian mixture model meaning that you could have a free Gaussian distribution in same noises, in a same noise distributions, and you get just given a different weightings, different means, and different standard deviations. So we're trying to model the pseudorange error, and here we call it a true pseudorange model. Pseudorange error, but it's not necessarily the true. What we get the true pseudorange error is that we do a double difference approach, which is using single difference to remove the receiver clock, and using another the difference between the reference station and the rover to get rid of systematic error. So the residual, we call it a true pseudorange error. Okay, so if we're trying to model the true pseudorange error out of the data that we collect, and we only considered 30 seconds of the window. This is what the error distribution look like. You have 3 Gaussians with a different weighting, 3 Gaussian with a different weighting. Okay, so if we trying to model the pseudorange residual, estimated by Pfeifer graph, we also using the 30-second window to calculate the distributions of the pseudorange residual of 30 seconds. This is how it look like. If you take a quick comparison, the mean is quite similar, the weighting is quite similar, and the standard look quite similar. So you can see the whole distribution looking quite similar, meaning that your FGO using 30 seconds window can model the error pretty well. And if we're using a batch, which is 250 seconds to model the whole pseudorange residuals, then this is what the distribution look like. So you can see the shape obviously very different from the actual one. So that's the reason why if you including more data, it's not necessarily being better, because your data is a bit outdated and you cannot represent the current environment. This is what we found. Okay. And another thing that people all care about is that, okay, what's the computational load of FGO? So obviously, it's the EKF, computational EKF is much smaller compared to FGO. I already explained, because we have a lot of constraints and lots of data all taken into considerations. But the real question we try to answer is that, can the FGO for real time? So our quick answer is yes, if the window is applied. So this is the second we use to calculate the data. If you using the batch approach, okay, and you have the two very different optimizers. One is GT-SLAM, one is I-SLAM, and you can see that the computation loss of the GT-SLAM is actually much higher than the I-SLAM. I'm not sure if I make the color incorrectly. This one could be blue, could be red. This one could be blue. But what I'm trying to say is that actually in the new nonlinear optimizations solver, they actually can solve the problem much faster than before. So meaning that even if you got the 10 epoch of the data, you can still process in a second level. Okay, so if you want to know more about the computation law, please, and how to reduce the computation law, please go and read these 2 papers. You can find the details in my journal papers, or we can have a Q&A session there later to discuss this. All right, so quickly conclude, because I already spent 35 minutes, that we conclude that, okay, EKF and FGO, they owe some Gaussian distribution. EKF, they apply the first order Markov chain, but FGO did not. And FGO solved the problem by iterations, but EKF did not. And these pros and cons, we also experimentally proved. But for future works, that we find out that GMN can use to model GNSS in urban Kenya. We should do it. But what window size should be used if we wish to adaptively turn the GNN model? And what factor to consider when we adaptively adjust the window? The environment, maybe? Sometimes it's open sky, sometimes it's urban Kenya. That is the question we're trying to answer later. If you're interested about how we can using GNN to model, using FGO to model, to effectively model the GNN errors, you can check our paper in Plans 2020. And this is the Dr. Weisong working with the team in 2020. Sorry, in 2020. A very interesting paper. I strongly suggest you read. And if you're interested about implementing FGO, so actually our latest paper we published in IEEE ICRAD 2021 is the open source call for GNSS-FGO. So in this GNSS-FGO, we not only give you pseudorange, we also using the Doppler. Instead of INS, we're using Doppler to connect the 2 different epochs of the state. And we also have the carrier phase model there. So because we're also trying to see whether we can using FGO to get a better flow solution for RTK. And the answer is yes. So you can also read the paper to find more. And if you're interested, this open source C and C++ code is available in GitHub. You just Google the paper and you should be able to find the informations. Okay. And one last, just using one last few minutes to do an advertisement a little bit. So actually, ION. So I proposed an idea in ION and also IAGs that we're trying to open source the data we collect in Hong Kong urban Kenyas and also Tokyo urban Kenyas. In Tokyo, you have Odaiba in Tokyo and Shinjuku in Tokyo. In Hong Kong, you have Mongkok, you have the Chinsazhui in Hong Kong. If you're interested, search Google urban nave. Okay, so in this data, we have a bunch of different LiDAR sensors, and we have IMU with a camera, and we have a different level of GPS receiver, and we provide you the ground truth. And also, if you're interested about using RTK, then you have the base station data to download from the Hong Kong Land Department. So this is our setting. So you have lots of LiDAR point cloud to use, and you have the stereo cameras, and you have different level of GNSS receivers. Okay. And if you want to know more about the open source data, please sign up to ION GNSS Part 2021. So I'm going to give an introductions on this data set and how to use it and what's the feature of the data and how to use the GitHub to get the data. This is what I'm going to show. And if you're using our data, then maybe you can consider to submit a paper to ION Pacific PNT 2022 that we have a section inviting the work to use the data, the OpenNAV data, open source data to test your own algorithm. So we're trying to make this open source data as a new benchmark for different urban positioning method. And there will be all. Thank you very much. I want to, before I end the discussions, I want to thank Dr. Weisong to do a wonderful work so that I can share you the insight on the FGO comparison with EKF. Thank you very much. And I'm ready for the questions. Am I speaking to myself?
Nope, that's great. Thank you so much, Lita. We appreciate it. And we do have a number of questions from the audience that we will try to address. The first question is from Paul. He asks, in EKF, there is some outlier detection scheme with prior innovation test. Is there something equivalent with FGO?
Oh, I will say yes. So basically, if you can calculate the residuals, if you can calculate the residual can be used as an indicator to detect the outlier. And actually, if you consider to do the fault detection exclusions using FGO, you will find out that, okay, wow, so the numbers of measurement that you got is much more compared to EKF. So the real questions to ask is how can we quickly to exclude the faulty measurements, because now you have tons of measurement to exclude. If you run out all the tests, or the computation load is going to be crazy. But a quick answer is yes. Yes, Paul. If you got the residual, you should be able to do the same.
Okay, great. Next question is, as FGO requires batch processing, can this be used for real-time positioning?
Yes. So in fact, FGO is nothing new to propose. Actually, used in the robotics field for 20 years, I would say. In the robotic field, what they do is like, I'm not sure if I can explain this question better than my first author, Dr. Weisong. So Rick, can I invite the audience to speak? Is that possible?
Yeah, who is it that you would like to bring on? We can give them.
Weisong, can you raise your hand so that you?
Oh yes.
That's great.
Yep. Hold on one second.
So yeah, he knows better than myself. But my quick question is yes. So they can do a lot of the window approach to marginalize the previous error factor, to make the previous error factors also have very similar to what EKF do. The error factor can be the effect of the marginalized factor can be taken into considerations by metrical marginalized vectors. So please, Weisong, go ahead and answer the question.
Okay, thank you, Dodge. Thank you for a good presentation. So two solutions to solve the computation load. The first one is like we can do the sliding window together with the marginalization to marginalize the measurements outside the current window. This is the first technology to solve the computation load. The second one is using the incremental smoothing technology from the ICM that introduced from Dr. Xi's very
beginning of the slide, right?
Yes. This is
Let me show you the paper.
So
the
first answer is like it should not be a big problem to run a real-time performance if you use error marginalization or ISM using incremental smoothing technology. Yes.
So two keywords for you to take home to try. One is incremental smoothing. The second one is the marginalizations.
Yes. Marginalization, yes.
Okay.
Okay, great. Thank you both. Next question is, I've noticed that in your paper, the orientation is just the output of AHRS,
yeah,
which to my knowledge is also a filtering framework. Have you also evaluated a pre-integrated IMU model, which are built in GTSAM to estimate the global 3D orientation?
Yes, we did this in the visual and the inertial integrations. Visual, so we call it like VINS, visual inertial navigation system. Yes, so it's completely doable. It's completely doable. But in here, we don't want to include the pre-integration because we want to make it look simple so that we can understand what's going on behind. But the answer is yes. Yes, mechanization can definitely use, and we should use, in fact, and we should use. Yeah.
Great. Next question, did you use full covariance or diagonal covariance matrices for LC?
Oh, you mean like the, can you repeat the questions again, Rick? Sorry.
Certainly, yeah. It says, did you use full covariance or diagonal covariance matrices for LC?
Diagonal for LC, yeah. Diagonal covariance matrix for LC. And the diagonal terms are etched up multiplied by UERE.
Great. Next question is, have you tried to use an adaptive window size, and what would be the criteria to choose this window size in real time?
So yeah, so we haven't tried, but we strongly believe, my own belief. So there's a this is very interesting questions. So like our second author team, so he believed that the window size should be a parameter to be optimized by the optimizer. But that is very difficult. He's trying to still derive in the model. I'm not sure what's his progress now. Maybe, yeah, we can follow up this later. Team believe that we have to adaptively choose the window size by optimization approach. And myself, I think, yeah, another way we can dealing with the adaptive window is that maybe, because for me, I'm doing multipass analysis for a couple of years. That is strongly related to the environment. And another string of research is that I also get the talk a week ago on using AI and GNSS. So what I believe is that we can use in the context awareness, for example, the research developed by Paul Gurus, we can use in the context awareness to define, okay, for example, in open sky environments, and we set the window size as 200 until that your machine learning network, deep learning network tell you that you are changing to another context. Then you're starting to give another constant size of the window for the FGO. That is why I believe we can try, but we haven't because this is actually related to a lot of deep learning issue. The data is general enough and the model is general enough, so lots of issues to be coped with. So a blue sea research over there. Yeah.
Okay, great. Thank you. Next question is from Fabian at Stanford, who asks, hi, Fabian, by the way. He asks, first, thank you for the talk. Have you considered including temporal measurement correlation in the FGO algorithm?
This is very interesting point. Like actually for FGO, if you're using a batch approach, okay, I'm talking about batch approach, if you don't use the incremental smoothing or marginalization, using a batch, then actually all the time correlate effect are iteratively are considered in the batch optimization already, because in our optimization, everything, the time correlate stuff, everything are inside the model. In the other words, if you're using batch, it's more or less like a snapshot estimation. It's like a snapshot estimation, meaning that the time correlate effect inside the models is already being copied with the error function, with the factors here. It's copied with the factor here. So we do believe with the features of FGO, this is one way that we can do a snapshot positioning, and this snapshot positioning can be used for integrity monitoring later. Okay, so because EKF is very hard, you need to consider time correlate noises, and that is always very difficult to model, always very difficult to justify that your covariance actually cover the noise. But for FGO, because if we're doing batch, again, I'm emphasizing, if I'm doing a batch, the time correlation between two epochs of the time, the state, is being considered in the model already. So it can become a snapshot estimation. So we believe it can be used for the next step of the fault detection, exclusion, and integrity monitoring for the integration scheme. Not limited to GNSS and INS and to the other all source navigation. That's possible. So we also submit one paper to Ion GNSS Plus 2021. We hope we can share you more on what I just mentioned. Yeah.
Great, thank you. Question from Daniel. He asks, did you compare your method with an unscented Kalman filter? To my understanding, classical Kalman filtering and your methods will be totally equal if both state and measurement models are linear. So your method has impact for non-linear models only?
So the first question is, have we tried unscented Kalman filter comparing with FGO? No. And sorry, the second question is?
Let's see, and you can open up the Q&A tab if you want to read along.
All right.
The question there. He says, does your method have an impact for non-linear models only?
Your method totally equals if the both statements are linear. So your method has the impact for nonlinear models on. So your method has impact for nonlinear models only. Yes. So if we have linearized models and they are all Gaussian noise. They are all Gaussian noise, that EKF and the KF and FGO give you the same result. Because they are all maximal posterior estimation, they give you the same result. Okay, so but it's not only the nonlinear models, it's about the noise distribution. The noise distribution. If you also put my method has the impact for nonlinears and the non-Gaussian, that would be what I trying to argue here. Okay.
Great.
I hope I answered the question.
Yep. Let's see. I just want to scroll down here and look. If you or Weisong see a question you'd like to address, also you can look through these and answer those as well.
Okay, so Weisong, feel free to do so. Okay, you are the first, also you know better than myself. So I just go one by one, or
yeah, we can. Hold on one second. We did have one in. Let me translate. Give me.
Okay. Can you specify if we can apply the innovation sequence monitoring to? I think yes, we can use in innovation sequence to check the outlier, as I mentioned the previous answers to Paul. Yes. Because in my implementation, it seems that the estimation slope show less accuracy comparing to position. We to use like pseudorange and delta range. So what's the previous questions of this one? If it interests you, you can write me an email to write down your questions, maybe in detail. Then I can answer better. What about the estimated state covariance? EKF is usually not constant, error 3 sigma. Is it better? What about the estimate state covariance? So, Weisong, are you there? Can you give your view on this one? This is
yes,
a very interesting question.
So which question? Which question?
Can you see my screen?
Okay.
It's the question by Paul at 11:35.
Yeah. What about the What about the estimated state covariance matrix? That one.
Okay, 11:35. I cannot. Oh, what about the estimated? What about the estimated state covariance matrix?
EKF is usually not consistent. Yeah, is it better with? I think yes, but I don't have a very strong argument to this. My instinct is yes, but I don't have a very strong argument to this. Do you have more insight to share with us?
I mean, EKF is usually not consistent. I'm not sure what do you mean by EKF is usually not consistent. Is it better with FGO? You mean whether we do the outlier rejection based on the 3 sigma threshold or something?
I think the question is that the state covariance matrix, the P matrix, is usually not consistent. Yeah, but yeah.
We didn't look into the covariance of the estimated states currently. But I
Yeah,
think
we
it's
have
interesting to look into the estimated covariance of the state to see the difference between the EKF and FGO. But from my view, the covariance from the FGO should be smaller than the EKF because you get more data, get more historical data. Should be. Yes.
But our gut institution is yes, but we don't have a proof. Yeah, we don't have a proof.
Yes.
Okay. Carry some.
I think we have time for one or two more questions.
So I just go.
Yep, you can read the questions as you've
okay.
seen them there.
So Carrie-san asked, first of all, FGO does not need to assume Gaussian noise. Yes, I agree with Carrie-san that FGO does not need to assume Gaussian noise, but we're trying to what should I say? I'm trying to make it as a proper comparison to EKF. Okay, but if we also want to consider that it's non-Gaussian noise distribution, you can check our paper in Plains 2020. Actually, we assume that it's a GMN instead of a Gaussian noise. One of the weakness of FGO is not able to quantify the uncertainty of the state, such as noise covariance. Do you have any thought? So this question is very similar to what Paul just asked. So I think this question we cannot answer now. We need to, we definitely have to dig into it. So Rick, can I have one more?
Absolutely, okay.
Yes. Can I answer the last question? The last question is like, it's John's.
If I understand the, so I will answer William's questions. If I understand the presentation correctly, Doppler measurement were not used in the, we didn't use the Doppler in this paper, William. Have you looked using the delta range or carrier phase in addition to pseudorange when comparing FGO and EKF-E? So this, so please check our paper in ICRA ICRA 2021. So in that paper, we do use the delta range, which is the Doppler frequency and carrier phase, and comparing, I'm not sure if we're comparing FGO with EKF, but we do use the Doppler frequency and carrier phase in the FGO implementations. Okay. And for Ho Min's questions, thank you for the thank you for your presentations. In our research, we have observed that one of the drawback of FGO for the state estimation is the optimization eager to rely on new coming measurements in its own natures. It can poison the reinitialization, especially in ISLAM2 settings, so that the huge state bias can be expected. While the filtering bias method rely on global motion models, in the other words, IMU and strip downs, which just be corrected. Have you also observed these phenomena, and what should be the solutions in your opinions, fusion or of more measurements? So the first question is they can poison the reinitializations. So yes, this would be true if we are not talking about GNSS-INS integrations. For visual odometry integrate with inertial navigation system, yes, this can definitely poison reinitialization. But for GNSS, because for GNSS, the model that we use is very much easy to linearize because satellite is very far from the receiver. So the linearization part is not an issue for this particular application, GNSS-INS integration. But for the other application, yes, you are 100% correct. Okay, and the second question, while the filtering-based method relies on the global motion model, which just be corrected, have you observed the same phenomena? And what should be the solutions in your opinions? I don't know how to answer the second one. Maybe Weisong, you can try to answer the second one.
While filtering, I'm not sure what do you mean by relay.
Weisong, we lose you. Have you observed this for now?
Global motion model. I'm not sure what is the global motion model here.
I'm used strip down system. Just be corrected. Fusion of.
Just be.
Sorry,
you can send an email to me to. Okay.
Yeah. To answer, maybe we communicate by email. It will be easier for us.
Yes, you can structure your question in more detail because from your text I cannot catch your questions here.
Okay. So Rick, I guess we are about time, right? So 5 minutes to the game of Spain versus Croatia. So yeah. maybe
Yes, no, you guys have done great. We appreciate it so much. And we recognize that we can't get to everyone's questions. I know, Lita, I think you had a slide with your email addresses. Would you
pull
that up?
Yeah, please. Oh, sorry.
Again, the paper is available for download from our website at ion.org. If you go to publications or under technical content, and you look for the journal in volume 60, you were in volume 67 last year. But here are the email addresses of our authors today and presenters. We appreciate both of you for being here for your presentation and for answering the audience questions. So again, thank you for joining us today. We look forward to having you join us in a future webinar. Thank you, and have a good evening over in Hong Kong. And if you're here stateside, have a good day, good evening, wherever you may be. Thank you.
Thank you. Thank you, everyone. Thank you, Rick.
Thank you, everyone.
Okay. Bye.